Hello people, very good evening. With immense pleasure, this is Prasanna R from IIT Engineering College and I'm a PhD scholar in Anna University. And my supervisor is Dr. K. Annaram from Jerusalem College of Engineering. My presentation title is a novel method for proteomic test using UWB antenna. So proteomic test is a test which is used to detect the clotting time of the blood. So with this UWB antenna, I'm going to detect that. Before going in depth with this particular topic, my research topic is all about creating a UWB array using balloon feds and MEMS switches. So why UWB? UWB is the best answer for all the problems which you are facing in wireless communication because of its wonderful features such as wide bandwidth, fine-time resolution, and the very important point is it has a very low transmit power. And apart from it, the very important thing is it has the capability of communicating and positioning in the same technology, in a single technology. It makes it very vital for wide applications, such as you can see it can be used in a lot of applications like RF networks, wireless sensor networks, communication electronics, and as well as RFID, even in UWB radar. And with this particular applications, we have all these applications advantage comes with single disadvantage, which is the interference which we are facing in UWB. So my area is I'm going to design UWB array which is going to suppress that particular interferences. I would like to give you a very practical example for this particular thing. You will be having, everyone will be using a laptop where we can able to access the Bluetooth and as well as the Wi-Fi using the laptop. Which means for Bluetooth and as well as for Wi-Fi, you have a separate single antennas which has been integrated in the laptops. With UWB technology, you don't need all those antennas. With single antenna, you can able to integrate Bluetooth and as well as Wi-Fi and as well as UWB. And another example is if you are going to use a digital camera, you don't need a computer to take up the printout of the pictures which you're using. We can directly connect with printers and you can take pictures of those in digital camera, and that is the greatest advantage of UWB. So these are the drawbacks which we are facing in normal narrowband problems, that is multipath fading, insecure, poor range resolutions, and limited data rate. All this disadvantages comes with one particular feature of narrowband, that is bandwidth is very, very narrow. And to overcome all these problems, you have answers for all these problems in wideband. Data rate and low power and fading robustness. It has the penetration capability, which means its central frequency is very less, so that you can able to penetrate through various materials. And that particular feature is very, very important for UWB radars and also for military applications. And you can see the diagram here, the bandwidth of UWB is very high. And you can see the spatial capacity of UWB antenna. It is the highest spatial capacity when compared to all other wireless standards which is available right now. And with all these advantages, the main problem in UWB is its interference with the existing wireless standards. That is, already we have a lot of wireless standards like IEEE 802.11 and as well as Bluetooth. All the standards have strong interference towards this UWB. That's because everything comes in this particular band. The UWB band frequency is 3.1 to 10.6 gigahertz, and within this frequency range you have a lot of interferences. These are the known interferences with UWB, and you can see the major interference sources are Wi-Fi and WiMAX, which is 3.3 gig to 3.7 gig and as well as 5.2 to 5.8 gig. And this is the major interference sources. And you can see all of the other interference sources like 9.2 to 9.5, which is also a major interference sources. So with this interference, now we can understand the main objective of UWB, creating a UWB array, is to overcome this particular interferences. So in order to overcome this interferences, a lot of research papers has been published, and we can able to overcome this interference by using two features. One is reconfiguring the antenna, that is reconfiguring features, or else frequency notching characteristics. Frequency notching characteristic in the sense neglecting that particular frequency alone, and that can be possible with a lot of technologies. For example, if you take frequency reconfiguration, a lot of papers have been published in order to reconfigure an UWB antenna by using MEMS switches, pin diodes, varactor diodes, and using various filters. And apart from it, you can also see a frequency notching characteristics, which means by using a different slots antenna, by creating a separate slot in the radiating part of the antenna. It can be of any slot, U-shaped or H-shaped or any particular slot which is mentioned here. You can see all the slots, and also you can use bars which has been attached or something like that, which can also create a frequency notching characteristics. So what I mean is we can able to reconfigure an UWB antenna by using all the switches, or we can also create a frequency notch characteristics with this particular design. And this is these are the literature surveys which I have done so far, and with this I'm going to design a particular UWB array using a balloons and MEMS switches. The reason why I have selected balloons is because of its feature of converting an unbalanced signal to a balanced signal. And the main function of the balloon, as you can see, it provides impedance transformation and also balanced to unbalanced transformation. And you can also see, I'm going to use MEMS switches. I can see a lot of diodes and other things has been used for reconfiguration, but my choice will be to use MEMS switches because you can see it produces low loss and as well as it has excellent isolation in wideband response. These are the techniques so far which has been proposed for improving the performance of UWB antenna, and these are the the first technique is frequency selective surface, which means it is a thin selective surface which allows the rays to transmit, reflect and as well as absorb. But the main disadvantage with this particular technology is its complex interactions with the antenna. And then you have electromagnetic bandgap structures and photogenic bandgap structures. What is bandgap structure? Microwave bandgap structure, which has been a systematic arrangements of electronic and magnetic bandgap structure, which is capable of creating a stop band in microwave, and that is called as bandgap structure. And with this bandgap structure, we can able to manipulate electromagnetic waves to a great extent, which is not possible so far. And this particular technology, electromagnetic bandgap, will help you in increasing the efficiency and gain of an antenna, whereas in photogenic bandgap antenna, it is help you to increase the directivity of the antenna. And the last technique which is being used is defective ground structures, which is right now we are using this particular technology. That's because you have a lot of advantages in this particular technology. And you can, from the name itself, you can understand it is called as defective ground structure, which means by creating a slot or edging the ground structure of the particular antenna, we can able to improve the performance of the antenna. The antenna performance can be improved through gain, efficiency, directivity, polarization. Everything can be improved by using defective ground structures. These are the design techniques, and these are the literature survey which I mentioned before. You can see the methodology which is being used for reconfiguring. You can see patches, resonators, filters, diodes. Everything has been used in order to reconfigure an UWB antenna. With this particular design structures, I have personally designed one particular antenna. It's not a reconfigurable antenna. This is a simple antenna which can be worked in UWB range. And my suggestion, my observation was, I was just trying to use this antenna for a medical application, and I could able to see wonderful results in testing prothrombin time of the blood. This is the single antenna which I have designed, and this is a flexible antenna, of course. And you can see this is the testing process which I have done using the blood, and you can see the prothrombin blood time, the time needed for clotting the blood. That has been tested in prothrombin test, and I have done using this UWB antenna. You can see the radiations here. You can see the radiations of UWB, and this is the frequency spectrum analysis of that particular radiation. And this is the simple analysis what I have done so far. This is just at the initial stages, and you can see a very good correlation between the result which is absorbed through lab and as well as through radiations. You can see this is the particular highest prothrombin time. The normal prothrombin time for a human being is 12.2 to 12.8, and you can see this is the highest prothrombin time mentioned in this particular sample to reach here. And first of all, I would like to thank IIT for giving such a wonderful opportunity for us. Everything was well planned and everything was up to the mark. Especially lunch was today, it was very great. And the presentation today, I had a lot of insights from, especially that Mercury presentation from the professor. It was very inspiring. I'm I'm a lover of public speaking. I was really astonished with that presentation. Thank you very much for that beautiful presentation, sir. And thank you very much. And particularly, I have to say special thanks to Professor Arun Chakravarti, because from IIT, I couldn't be able to see such a humble person. He invited us today morning and he helped us to register. I have never seen such a humble person in such a wonderful forum. Thank you very much, sir. And I thank all the eminent personalities here for sharing their insights and giving us such a wonderful opportunity. Thank you very much.